So, welcome student to the foundation of classical electrodynamics course. So, today we have lecture number 20. So, in the last class we discussed about few problems. So, we also going to continue with certain problems. So, the tutorial will continue here in this class as well. Today we have class number 20. And we were discussing tutorial. So, this is tutorial and this is continued whatever we started. So, few more problem we will going to discuss. Okay. So, let us so 3 problem we discussed last class. So, let us do more. So, today we will start with problem number 4. And the problem number 4 is this: let A is equal to yi, a vector field is given yi plus z j plus x k. A vector field is given in this way. Now, the question is, find the flux of A, of vector field A, through the surface y equal to 1 and for x 1 to 0 and z 2 to 0. So, this is the surface for which we need to calculate the flux. Flux is nothing but we need to do the surface integral here for this A vector field, but before that we need to first find out the surface through which we need to calculate this surface integral. So, this is my coordinate system. So, this is my x, this is y and this is z. So, the surface is such that y is constant. So, it is parallel to xy xz plane and also the value of z is goes to 0 to 2. So, I can first draw that. So, 0. So, x is 0 to 1. So, x is 0 to 1 from here to here. So, I can have 0 to 1, but z is 0 to 2 like this. So, this is the surface we are talking about. So, this point is obviously 1, this point is the coordinate of this point is 0 1, coordinate of point is 1 1 and coordinate of this point here it is 1 2. Okay, 3 dimension, I mean I need to put the 3 dimension also. So, it is 0 here. So, this is 1 1 0 here, make it correct. It is 1 1 0 here and this coordinate is x is how much? X is 0, y is 1 and z is 2. Okay, so, this is the surface, also we have this coordinate, but anyway. So, this is the surface through which I need to calculate this vector, the flux of this vector field. By the way, what is flux? The flux d phi is A dot the area, okay, this elementary area. So, here what kind of area we are having? ds here is how much? dx dz in the direction of j, because this is the direction of the surface, which is j unit vector. Okay. So, that quantity I can calculate, and A we know this is y I plus z j plus x k, right, dot. So, this is precisely, this is the A value I wrote here, and ds here is dx and dz with the unit vector j. So, from here you can see that I dot j will vanish, j dot j will stay, k dot j will vanish. So, eventually I have j dx dy, this is the amount of flux, tiny amount of flux d phi. Now, I need to calculate the total flux. If I calculate the total flux phi, which should be the integration of d phi, and if I do the integration here, so there is a z. So, sorry, this is not dx dy, this is, I am making a mistake here. So, this is dz. So, I can have this integration, I can have 0 to 2 and then z dz and this integration dx, x is changing from 0 to 1, and we are done. So, this value if I integrate, it is z square divided by 2 with the limit 0 to 2 multiplied by x with the limit 0 to 1. So, it is simply 4 divided by 2 multiplied by 1. So, the value is 2. So, the amount of total flux for these given vector field for this surface is this one. So, eventually we just calculate the surface integral here. This was our problem 4. Okay. Let us now continue with a more typical problem. So, let us take a little bit lengthy problem. So, the problem is this. So, this is problem number 5, and the problem number 5 is like that. Determine the flux, determine the flux of a vector field D, but this vector field is given in a different coordinate system. Note it, rho square cos square phi rho unit vector plus z sin phi phi unit vector over the closed surface of the cylinder and the cylinder is defined in this way: 0 z is changing from 0 to 1 and rho is equal to 4. That is the thing, that is part 1 problem. The second part of the problem is saying that verify, that is interesting, verify the divergence theorem for this case. Verify the divergence theorem for this case. Okay, that part is interesting because we need to verify everything. So, first we want to find out what kind of surface it is. So, as usual I have a coordinate system here and this is a cylindrical coordinate. So, and the cylinder and the closed surface is a cylinder with this. So, I can just draw it and it should be something like this. Okay, so this is the cylinder where this height, it is z, is unit and the rho, whatever the rho is saying, this is 4 and this is the height which is z. So, roughly this is the cylinder and this is a closed surface and we need to calculate first the flux of the closed surface. So, how many surfaces are there, first we need to calculate. So, first, so what I need to calculate, the closed surface integral, that is the flux. So, my calculation is this, I need to calculate d dot ds. I need to calculate this with the closed surface integral. So, this quantity, know that it is with the combined with 3 surface, one is this one, upper one and lower one. So, I need to divide this 3 surface. The total surface can be divided into 3 parts, S1, S2, S3. Now, for S1, surface S1, I can have the surface element ds1 is equal to rho d phi d rho z unit vector, okay, upper surface. For lower surface, that is for S2. So, let me write it, otherwise you may. So, my S1 is this one, my S2 is this 2 and this is my S3, this entire surface. So, next for S2 I have ds2 which is equal to minus of, because it is a lower surface, rho d phi d rho z unit vector. And finally, for S3 we have ds3 and that is rho d phi dz rho unit vector. Okay. These are the 3 surface element of the cylinder. You should go back and check the surface element, and now I am going to execute the entire integral for this surface. So, my total closed integral will be equivalent to this. surface 1 and then field, and the field is rho square cos square phi rho unit vector plus z sin phi phi unit vector dot ds surface, which is rho d phi d rho z unit vector, that is surface 1. What is surface 2? Plus surface 2, same quantity here, rho square cos square phi phi unit rho unit vector, the vector field which is given here, I am just writing that z, sorry, not cos, sin, z sin phi phi unit vector dot, there is a negative sign, mind it, rho d phi d rho z unit vector, and finally the third one rho square cos square phi rho unit vector plus z sin phi phi unit vector dot rho d phi dz rho unit vector. Now, it looks very clumsy and very big, but you can see that here z unit vector should be dot with rho and phi. So, this element will be 0. Simply I can write this is 0. Z will be dot with rho, z will be dot with phi, 0. So, the contribution that we have here rho, rho and rho phi. So, the contribution what we have here is rho cube integration of, so this contribution, these and this contribution will be there. So, rho is constant here, so I can put it outside. Then we have dz, so I just put dz, which is having limit 0 to 1, and then integration cos square phi d phi cos square phi d phi, which has a limit 0 to 2 pi. Okay. So, if I execute that, it simply gives me the closed line integral, closed surface integral, simply gives me rho cube into 1 into, this is half into 2 pi. If you execute that, you will get this. So, this quantity rho is 4, rho is 4. So, it should be 4 cube and pi. So, it should be 64 pi. So, that is the result of the problem 1. Now, the next part of the problem is saying that please calculate verify the divergence theorem. So, you need to verify it. So, what is divergence theorem? Let me write it first. So, divergence theorem is, if I have divergence of a vector quantity over a volume, that should be equivalent to the closed surface integral of the surface that is enclosing the volume. Okay. So, please check it that we have already figured out this part, right. This is 64 pi, that is the thing precisely we are calculating so far, the closed surface integral, the flux of. So, now if I calculate this quantity over the given volume and this value, if 64 pi, if it comes like this, then we are done. So, first we need to calculate this quantity, divergence of the given vector field D, whatever the vector field D is given, that. So, it is in cylindrical coordinate system, so you should be careful enough. So, that quantity is 1 over rho del rho and then rho square cos square phi, that is the first component, plus 1 by rho del phi, then z sin phi, and the phi component is not there. So, you can see that there is no z component. So, I should not have the z derivative here. Okay. Now, if you execute it, it should be simply 1 by rho, you are making partial derivative with respect to rho here. So, rho cube. So, you have 3 rho square and then you have cos square phi. What about this one? 1 by rho is already there, you have z and partial derivative with respect to phi. So, you have cos phi. So, eventually this is cos phi. So, eventually you have 3 rho and then cos square phi plus z plus z by rho and then cos phi. So, after that, so this is the value. So, dV, so this you calculate, but you need to calculate this quantity. You need to calculate this quantity over dV. So, first this I calculate here. So, dV we need to calculate, and this is a volume element in cylindrical coordinate system, and it should be rho d rho d phi dz. This is the volume element. Okay. So, now I calculate the total volume integral. Now, I calculate the total volume integral. That means, I calculate integration volume and then this quantity that we derive, which is 3, let me write it nicely. So, I should have 3 rho and then cos square phi and plus z divided by rho and then cos phi and then rho d phi dz. Okay. This is the integral, and now this integral I need to calculate. So, if I now gather everything, so 3, then the rho part. So, this is rho square d rho with the limit 0 to 4. Then we have integration of 0 to 1, then dz. Then we have integration 0 to 2 pi cos square phi. That is the first part. What is the second part? Second part is 0 to 4 and then rho d rho and then z dz, the limit is 0 to 1 and then 0 to 2 pi we have cos phi d phi. Okay, we are almost there. So, we have 3 rho cube divided by 3 0 to 4 multiplied by z 0 to 1 multiplied by half into 2 pi and and plus Here if you look carefully, that you will see this is cos function and I am integrating 0 to pi. So, it should give me 0. So, it is simply 0. So, what is this value if I calculate? So, this is 3 will cancel out. So, we have 4 to the power 3, 4 to the power 3 plus sorry, not plus, multiplication. So, multiplication by 1 and multiplication by pi. So, which is nothing but 64 pi. So, this is the same result we get earlier. So, this value I calculate 64 pi, which is equal to this quantity d dot ds. So, which proves which basically establish the divergence theorem. So, we can prove, we can show that the divergence theorem is correct. We verify the divergence theorem here. Okay. So, whatever the time we have, let us quickly do the last problem, problem 6. And problem 6 saying that consider a vector a vector function rather is x j minus y I. So, this is the vector function. Okay. So, check, the problem is check Stokes theorem around the circle in xy plane having radius a. So, we need to verify the Stokes theorem for this vector field. So, if I now draw this surface first and then Stokes theorem means I need to do the closed line integral. So, it is a circle like this with radius a, and if I now plot the vector function here, then vector function if I plot, it should be like this. And then it is a rotating kind of thing. So, here this is rotating, the vector field is rotating like this, and we need to calculate the Stokes theorem. So, let us first find out that in order to calculate, so what is the Stokes theorem? Let me write. So, A dot ds over surface integral should be the closed line integral, sorry, curl of A dot ds. I am making mistake here. So, the curl of A dot ds is equal to A dot dl. So, first what is dl? Let us find out. So, dl is over this line. So, dl should be, the vector dl should be A d theta, A is constant, d theta and the theta unit vector, because it is over this line, right. So, these things is nothing but A d theta in terms of I j k, because my vector field is given in this Cartesian coordinate system. So, I need to make a transformation, how write theta in terms of unit vector in terms of I j k. We did it earlier. So, it should be I sin theta plus j of cos theta. Okay. So, now A is x j minus y I, which is A cos theta j minus A sin theta I. Now, A dot dl, if I calculate, now I write A in terms of theta, and also this vector I can just make in Cartesian coordinate. So, A dot dl is A d theta and then this dot this. If you calculate this quantity dot this quantity, so the j dot j will be A cos squared theta and then I have plus A sin square theta, which gives me something like A square d theta. Now, if I make a closed line integral of this quantity A dot dl, it should be A square and the closed line integral, which is d theta ranging from 0 to 2 pi. So, my result should be simply 2 pi A square. So, that is the value I am getting here. When we calculate the line integral, closed line integral of this given sphere, given circle. Now, the next part is I need to calculate curl of A. Curl of A is I j k and then del x, del y, del z, then A x, A y, A z, and if I do the calculation, because A x, A y, A z, what is A x here? If I go back, so A x is minus of y. So, this value is minus of y. What is A y? A y is x. So, this is x and this is 0. Okay. So, this value, if I calculate I component, this is 0 and this is 0, j component, this is 0 and this is 0, k component we have 1. So, 1 and this is 1. So, we have 2 k, this is the value one can get. Okay. So, now you calculate the surface integral of this quantity dot ds. Now, what is ds here? Ds, it is ds in the direction of k. So, that means I am having integration of 2 k dot ds k vector. So, here we have 2 k dot k 1 integration of ds. Now, ds is a total surface, and if I am having a circle of radius a, then the total surface simply gives me 2 into pi a square. This is the area of the surface. Now, you can see this is the same value I am getting here and we are getting the same value here. So, that means I can write that the closed line integral A dot dl for this given circle is equal to the curl of A that we calculate over the surface, the surface integral, they are same, both the cases the value is 2 pi a square for this given problem. So, this is the verification of the Stokes theorem. So, we find that the Stokes theorem is valid here. Okay, so today we do not have much time. So, with this note I will conclude here, and thank you for your attention, and see you in the next class. So, where we start our module 2. Thank you very much, and see you in the next class.